Okay, and you kind of get bounded for free because the range here is all the valid functions. So that means you're never going to think you have a proof of something that's not valid. Okay. Right. So A is polynomially bounded if for every valid formula tau there exists an alpha such that the size of alpha is polynomial in the size of tau such that A of alpha equals tau. Okay. So we want proof systems, ideally like to have proof systems where for every valid formula tau there's a short proof, okay, where the proof has length polynomial in the size of the DNF. Okay. And if such a proof system exists, so this is an easy lemma or theorem. So there exists a polynomial bounded proof system if and only if NP equals co-NP. Okay. So you can think of this, so what is going on here? The set of all valid formulas that's a co-NP property. Okay. So if you have a polynomial time verifier, then you have an NP procedure for a co-NP complete problem. You just guess the short proof and verify it. Okay. So we think that there's no polynomial bounded proof system. Okay, that's a common belief. I'm not really so sure it's believable, but that's a different story. But today I'm going to tell you about specific proof systems that people study a lot. Frege systems, they're standard rule-based systems where you start with some axioms and some rules. And they can be algebraic, they can be more propositional. They're all very easily the propositional ones are all very easily seen to be polynomial verifiable. We'll see that the algebraic ones sometimes they're only verifiable in probabilistic polynomial time, so they lie. Well, we think that there should be polytime verifiers for them under assumption that you can do polynomial identity testing in polynomial time, but at the moment a lot of the algebraic ones are just polynomially verifiable. So we'll get to that later. Okay, so what we're going to do is study real proof systems. Ones that people study are much more restricted. They usually follow some specific set of rules. Proof is usually like a sequence of lines where each line is either an instance of an axiom or follows from previous lines by one of the rules, and the last line is the thing you're trying to prove. That's typically what they all look like. Okay. And the two things I want to try to drive home or convince you of is that by studying specific proof systems, so two things I want to focus on are so specific proof systems, lower bounds for them, basically rule out large families of polynomial time algorithms for NP-hard problems and even approximate versions of them. Okay, so we know that if you can show that no proof system is polynomially bounded, you've basically ruled out every algorithm. So you've proven, not only have you proven P not equal NP, but you've proven NP not equal co-NP. But I want to say that for specific proof systems like Frege systems, like sum of squares, systems that people study, the reason people care so much about them is because most of the algorithms that pretty well all the algorithms that we know of that have correctness proofs, so we know that they're valid, that they're good algorithms, all of those algorithms, kind of the correctness proof lies in some proof system, so it can be proved in some proof system, and therefore lower bounds in that proof system rule out a large family of corresponding algorithms. Okay. So that's one point I want to make. And the other point I want to make is that these proof systems, these specific ones, or almost all of them, have a dual form, a dual characterization. So it's like so all of the proof systems that we'll talk about, they have like two views. One is like a syntactic view, where I'm going to tell you there's a bunch of axioms, and I specifically tell you what they look like, and that's what the A is going to verify that it looks like that. Okay, and in the dual form, we'll describe if you don't have a proof, then there's some model. Okay, and the model in the algebraic case will be the pseudo distributions. In the propositional case, I won't have time to really fully spell it out, but they're kind of a model, more of a model theoretic construction.
There's no condition on what this algorithm should be. You can just do whatever.
That's right. So the thing that's kind of very disconcerting is that a propositional proof system could even be like Zermelo set theory with axiom choice, like anything you could conceive of that sounds incomplete. And it's it's verifiable, and it works with way more complicated formulas than just propositional ones. As far as we know, we don't have any idea whether that's even more powerful or not for just normal propositional statements. So it's really a kind of a conundrum.
There's no condition that says an algorithm should do something sensible. Like at the moment, it's just like a map between two things and something you follow.
Well, I'm forcing it to have range of valid formulas. So for example, you should think about some strings are going to be legal encodings of proofs. The illegal ones, what are we going to do with those? Well, typically they'll map to some trivially valid formula like x or not x. Okay, so it has to be somewhat sensible.
Propositional means what? Did it have no quantifiers?
Pardon me?
What does it mean at the point of the proposition?
Oh, I'm sorry. So propositional formula is just so the standard one is over binary and or not. Variables. The variables are formulas, and if it's like inductive definition. If f is a formula and g is a formula, then that's a formula, and that's a formula, and not f is a formula. No quantifiers. Yeah. So and a DNF formula would be like x1, x2, or x1, x2, or I'm trying to make this true, or x2, something like that. So it'll be a valid. Good. Okay, so I'm going to first tell you about
all right, So when I was preparing this talk, I decided that since the paper's out and since I gave a fairly standard talk a good number of times, I would switch it up a bit and give something a little bit different. Also, since this is a symplectic group that's not afraid of pseudo-holomorphic curves, I thought I'd spend some time talking about pseudo-holomorphic curves and those aspects of the proof. Still, though, I want to state the main dynamical result of this joint paper with Helmut. So everything that I'll talk about today is joint with Helmut. Right, so here it is. Theorem, consider R4 equipped with a standard symplectic structure and a smooth Hamiltonian, for which it's the case that if we define this manifold M as H inverse of 0, and this we want to be a non-empty, compact, regular energy level. And then under these assumptions, the Hamiltonian flow at M is not minimal. So let's see. So I'll explain this and we'll move on in a second. And I wanted to state this up front because this is sort of, in some sense, the big result, the big visible result from our paper. But in many ways, I think that for people more interested in symplectic geometry and topology, there's something else which is very interesting, which I want to spend most of my time talking about today, which is the pseudo-holomorphic curves which generate this result. But nevertheless, I want to sort of state this up front. This talk won't be too dynamical, though. So maybe you're looking at this result and you've forgotten or never known what it means for a flow to be minimal. And basically, a flow is minimal if it's the case that every trajectory is dense in the manifold. So what's an example of a flow which is not dense? Anytime you have a periodic orbit, right? Because that trajectory is sort of not dense, it's a periodic orbit. So this idea that right. So to say that a flow is not minimal, maybe we're saying there exists a periodic orbit. But if we knew that, then we'd say that, and we haven't said that, so that need not be the case. So right now, I mean, this is sort of one of the interesting things about this result, is that whatever it is that we find, it's some sort of, we guarantee the existence of a closed invariant subset, which is not everything. Yes, Dan?
Do you have an example without that periodic orbit?
Yeah, so we'll get to examples where we know that there exists no periodic orbits. We have to reduce the regularity on this, though. I have so reduce the regularity in order to get that, but we'll talk about that. Good. So in order to proceed, I want to back up a little bit, just to give a little bit of historical context, and say, let's see. Here's a question. Let X be a vector field on S3. Must it be the case that the flow associated to X has a periodic orbit? Question. And of course,
you mean by non-singular because it wasn't too long.
Well, must it have one?
Must have.
I mean, a constant. We can make it non-singular if you like. It's beyond.
So it's not
Non-singular means no or zero. And presumably you've seen this problem before. It's an old problem. It has lots of answers. This is Seifert asked this question. And in general, we know the answer is no. Basically, you can find vector fields of whatever regularity you like on S3 with the property that they don't have a periodic orbit. There's an exception, which is the Ray flow. So this is a flow generated by a Ray vector field. And in this case, we know by the results of, I guess so Helmut's 93 paper then sort of guarantees